Assalamualaikum dan salam sejahtera. Saya Cik Syariza binti Syahari, pensyarah fizik Kolej Matrikulasi Negeri Sembilan, akan mempersembahkan video pengajaran dan pembelajaran bagi kuliah fizik SP025. Selamat menonton. There are many applications of capacitor in our daily life. We normally use capacitors to reduce unwanted signals such as noise. The electronic devices such as TV, phone, radio, microwave, calculator, and etc. are never work without capacitors. In this chapter 2, called Capacitor and Dielectrics, we will cover 3 subtopics. The first subtopic, 2.1, is about capacitance and capacitors in series and parallel, where the second subtopic, 2.2, is about charging and discharging of the capacitors. And for the final subtopic 2.3 is about capacitors with dielectric. In this first subtopic 2.1, students should be able to define and use capacitance. The formula for capacitance C is given by Q divided by V, where Q is the symbol of charge and V stands for potential difference. In the same subtopic, which is 2.1, students should also be able to derive and determine the effective capacitance of capacitors, which is in series and parallel, and also students should be able to derive and use the formula of energy stored in a capacitor. As I've mentioned earlier, the electronic devices such as TV, phone, radio, microwave, calculator, and etc. are never work without capacitors. It is mainly because capacitor is capable to store electric charges or electric potential energy. It is consisting of two conducting plates separated by a small air gap or a thin insulator. The conducting plates could be in the shape of cylindrical, spherical, or parallel plate. The electrical symbol for a capacitor in a circuit could be drawn like this or this. Here are some of the common examples of the uses of capacitor in many electronic circuits. Okay, let's go deeper into what is meant by capacitance. Capacitance C is defined as the ratio of the charge on either plate to the potential difference between them. Mathematically, C is equal to Q over V, where Q is the magnitude of the charge on each plate and V is the potential difference across the two plates. Capacitance is a scalar quantity. The unit of capacitance is farad or coulombs per volt. 1 farad is defined as the charge of 1 coulomb stored on each of the conducting plates as a result of a potential difference of 1 volt between the plates. Bear in mind that capacitance is always in a positive value or positive quantity. From the equation we have seen before, we can see the relationship between Q and V. As the capacitance C of a capacitor is constant, therefore Q is directly proportional to V. Meaning that the greater the capacitance of a capacitor, the more charge is required. Figure 2.2 shows three capacitors are connected in series. Here is the battery. A battery of voltage or potential difference of V is also connected in series to the capacitor. This circuit is equivalent to the circuit which is much simpler as this one. For the series circuit which is complete, electrons are transferred onto the plate such that the magnitude of the charge Q on each plate is the same. The total charge on the effective capacitor Q is equal to Q1, Q2 and also Q3. The potential difference across each capacitor, which is C1, C2 and C3, are V1, V2 and V3 respectively. Hence, V1 equal to Q1 over C1 or Q over C1 because Q is the same for each of the capacitor. V2 equals to Q over C2 and V3 equal to Q over C3. Meaning that for the capacitor which is connected in series, the charge Q is equal for each capacitor, which is equal to the effective capacitor, but the voltage at each capacitor is different depending on its capacitance C. The total potential difference V is given by V equals to V1 plus V2 plus V3, where V equals to Q over C1 plus Q over C2 and plus Q over C3. Why this V equal to Q over C1? This is because from the previous concept, the charge of capacitor 1, which is Q1, equal to the total charge Q. That is why here we have the label for Q is only Q but not Q1. This concept also applies to V2 and V3. Therefore, the effective or equivalent capacitance C effective for n capacitors in series is given by 1 over C effective equal to 1 over C1 plus 1 over C2 plus 1 over C3, and the number goes on, depends on how many capacitors is connected in our circuit. Here, the combination of capacitors are in parallel to a battery V. So, in this combination, the supply voltage V equals to V1, V2, and V3. So the potential difference of effective capacitor is written as this equation. The value for Q1, Q2, and Q3 in parallel combination of capacitors are not the same anymore with the value of Q as what we have discussed in series circuit. In this parallel circuit, total charge Q is equal to Q1 plus Q2 plus Q3. And the effective capacitance Q is equal to C1 plus C2 plus C3 depending on how many capacitors are connected in parallel to the battery in the circuit. Now we move to the second part of subtopic 2.1, which is energy. At the end of this part, students need to know how to derive and use the formula for the energy stored in a charged capacitor. The symbol for energy in a capacitor is given by capital letter U as what is written here. A small amount of work is done in bringing a small amount of charge from the battery to the capacitor. This is given by delta W equal to VdQ. And because V is equal to Q over V, so we can have delta work or dW equals to Q over C dQ. The work done formula can be derived by using the concept of integration. The integration of delta W from 0 to W is equal to the integration of Q over C from 0 to Q with respect to Q. When we integrate dW, it will be U or W, and this U is equal to the results of above integration. The results of the integration of Q over C with respect to Q is equal to half Q squared over C. Or U is equal to half CV squared, and the last formula for energy is equal to half QV. These three equations or formula here can be used to find the energy stored in the capacitor. No charges will accumulate on each plate if the capacitor is not charged. So, if the capacitor is not charged, so there is no energy can be stored in the capacitor. Now we move to the next subtopic. The second subtopic is about charging and discharging of capacitors. At the end of the chapter, students should be able to 1. State physical meaning of time constant and use time constant, tau. Second, to sketch and explain the characteristics of QT and IT graph for charging and discharging of capacitor. And the third one, students should be able to use the equation of charge Q for discharging and charging process. Figure 2.11 shows a simple circuit for charging a capacitor. As what we can see here, there are a few devices and components that are being connected by a wire to complete the whole circuit. We have power supply V, or a battery, We have a resistor as to slow down the process of charging or discharging. We have switch S, and of course we have the capacitor itself to be charged here. When switch S is closed, meaning that the circuit is complete. Electron will flow out from the negative terminal of the battery and accumulate on the plate B of the capacitor. Meaning that electron from the negative terminal at the battery here will move in this direction to be accumulated at this plate B. Meaning that at this time more electrons accumulate at plate B and making plate B to be negatively charged. As what we have learned in chapter 1, same sign will repel one another. So the negatively charged of plate B will repel the electron from plate A, leaving the electron from plate A here and making plate A to be positively charged. Okay, so this is how plate A and B to be negatively charged or positively charged. Okay, we fast forward to the third point. Yeah, the first and the second point is actually has been discussed earlier. Okay, so as charges accumulate on the capacitor, the potential difference across it increases and the current is reduced until eventually the maximum voltage across the capacitor equals the voltage supplied by the battery. Okay, at this time no further current flow through the resistor R. At this particular time, we have to know the concept of current flow. Current will only flow if there is a potential difference. When both voltage at capacitor and voltage at the battery is having the same value, no more potential difference, so no more pressure to push the electron to flow as current. That is why there is no current flow through the resistor when the capacitor is fully charged. Okay, and we have the charge Q here. The charge on the capacitor increases until it reaches its maximum value. Yeah, so the charging process can be shown through the graph in figure 2.12a, 2.12b, and 2.12c at our next slide. Okay, we have three graphs here. We have VT graph, QT graph, and also IT graph. For this IT graph, the explanation is actually in our previous slide. For V and Q versus T graph, why there are actually increases over time? Because as in our charging circuit, when the charges is being accumulated in plate A and B, the voltage will be increasing until they reach their maximum value. Okay, that is why voltage and charge graph is having or is actually increases with time. Okay, so from the previous slide of graph Q versus T and V versus T, we can have this equation to be produced, which is 2.4 Q equals to Q naught in a bracket 1 minus e to the power of negative t over RC. And for potential difference, V equals to V naught in a bracket 1 minus e to the power of negative t over RC. Okay, so here I or current will have a slightly different in its equation because from what we have seen in the previous graph, I versus T graph is not equal to V versus T and Q versus T graph. So here I equals to I naught times E to the power of negative T over RC, where I naught equals to V naught over R. Figure 2.13 shows a simple circuit for discharging a charged capacitor. This circuit looks similar to the charging circuit, but the only difference, we do not have battery now to supply the charge. As the positively charged plate A is having excessive amount of positive charge, those charges will flow back to the negative plate B. This is because the opposite sign of charges is attracted to one another. So now we are going to analyze how V, Q and I changing with time. Figure 2.14a shows the potential difference across capacitor, which is decreases exponentially with time. When the positive charges on plate A neutralized by the electron, the voltage across the capacitor is reduced. This process continues until the current through the resistor is zero. The same concept of the current as what we have learned in charging process also applied here. At this moment, all the charges at plate A is fully neutralized and the voltage across the capacitor will drop to zero. Okay, we are going to look at our QT and also IT graph. Our figure 2.14b is exactly the same as 2.14a in previous slide because QT graph is exactly having the same shape as VT graph. Now we have IT graph, which is similarly like what we have in charging process. The only difference is the curve now is at the negative side of the graph, where I naught is in negative value. This is because the direction of current is in opposite direction as compared to our charging circuit. But if we are going to draw IT graph in positive side, same like what we have in charging circuit, it is also acceptable. Now we are going to look at all the equation that represents our graph of QT, VT, and IT graph. Q is equal to Q naught e to the power of negative t over RC for our charge. For our V, which is our potential difference, V is equal to V naught e to the power of negative t over RC. And last, for our current, I equal to negative I naught e to the power of T over RC. The negative sign indicates that as the capacitor discharges, the current direction is opposite to its direction when the capacitor was being charged. This is what we have discussed in previous slides. Now, let's look at our subtopic called time constant. Time constant is given by a symbol tau. The formula for time constant tau equals to RC. As in charging and discharging circuit having resistor and capacitor which is connected in series, so R is the resistance of the resistor and C is the capacitance of the capacitor. Time constant is a scalar quantity and its unit is second. It is to measure of how quickly the capacitor charges or discharges. Now we will go to the definition of time constant tau. Time constant tau is actually having two types of definition. The definition of time constant tau is for charging process and also for discharging process. The first point here is the definition of time constant during charging process, where time constant tau is defined as the time required for the capacitor to reach 63% of its maximum charge or maximum voltage. All the time constant definition here is actually came from the graph that we have discussed earlier. Here is our last subtopic for this chapter. It is about capacitors with dielectrics. At the end of this chapter, students should be able to define dielectric constant, which is the symbol epsilon r equals to C over C naught. Secondly, students should be able to describe the effect of dielectric on a parallel plate capacitor. The next one, students should be able to calculate capacitance of F-filled parallel plate capacitor with the formula C naught equals to epsilon naught A over D. And lastly, students should be able to use capacitance with dielectric C equals to epsilon R times C naught. Dielectric constant, epsilon r or kappa, is defined as a ratio between the capacitance of a given capacitor with space between plates filled with dielectric C and the capacitance of the same capacitor with plates in a vacuum C naught. Mathematically, epsilon r equal to C over C naught. There is no unit for this dielectric constant. Firstly, we have to know what is the meaning of dielectric. Dielectric material is the same as insulator or a non-conducting material. This dielectric material is placed between the plates of a capacitor. When a dielectric is inserted between the plates, the capacitance will be increasing. It is increases by a factor epsilon r or kappa, which is called the dielectric constant of the material. The advantages of inserting the dielectric between the plates or the effect of inserting the dielectric between the plates is number 1, increase in capacitance, increase in maximum operating voltage, and With decreasing in D, which is the distance between the plates, it will increasing the C. A capacitor can be considered to be in this parallel plate capacitor, where A is the area of the plates, D is the distance between plates, positive Q or negative Q to be the charges on each plate, and V is the potential difference between the plates itself. So here we can have the formula for parallel plate capacitor to be C naught equals to epsilon naught A over D and C equals to epsilon A over D. The difference between C naught and C naught is actually the capacitance for parallel plate capacitor in a vacuum, but C is the capacitance for parallel plate capacitor separated by dielectric material, where epsilon naught is the permittivity of free space, epsilon is the permittivity of dielectric material, and D is the distance between the plates. Also, A is the area of each plate. The equation for epsilon R is equal to epsilon over epsilon naught, where epsilon is permittivity of dielectric material and epsilon naught is permittivity of vacuum. From C equals to Q over V, we can have epsilon R is also equal to V naught over V. And here, from V equals to ED, so our next formula for epsilon R is equal to E naught over E, where E naught is electric field strength of the capacitor in vacuum, and E is the electric field strength of the capacitor with dielectric. The dielectric constant depends on the insulating material used. Table 2.1 shows the dielectric constant epsilon R for various material. Now we are going to analyze how the dielectric material will affect the value of capacitance C and also to other values. Figure 2.18a shows a parallel plate capacitor in vacuum. E naught represents the initial value of electric field in between the plates. Bear in mind, in this case, no battery is connected to the capacitor, as we want the value of charge Q to be constant. The capacitor is also fully charged to certain amount of charge. Okay, now we want to investigate what will happen if the dielectric is placed in between the plates. We can see here in figure 2.18b, the dielectric is placed in between the plates. The molecules of dielectric tend to become oriented with their positive end pointing toward the negatively charged plate and their negative end pointing towards the positively charged plate. You can see the negative to the positive plates and the positive charge oriented to the negative plates. Here are the new electric field pattern in between the plates after the dielectric is being inserted. This is because of the positive charge is built up on one surface of dielectric and of negative charge on the other. The numbers of electric field lines here in 2.18c is reduced or is decreasing as compared to figure 2.18a, which is before dielectric material is inserted. Se is lesser when we insert the dielectric in between the plates, so the potential difference is also become less. This is from the formula V equals to ED, where V is directly proportional to E. From C equal to Q over V, when V is lesser or smaller, with Q is constant or remain the same, the capacitance C is increased by the dielectric. This is the main effect when dielectric is inserted in between the plates of the capacitor. It will increase the capacitance of the capacitor. This is what we have in chapter 2, and chapter 2 ends here. Thank you for viewing and watching.
Jangan lupa like, share and subscribe video ini. Thank you for watching.